started. Let's see if there's anything to discuss. Lab this week, we're doing norbornene hydration, which is a hydration of an alkene. Our first reaction, first synthesis in lab. And we'll begin alkene reactions today. Question?
I have a question about the lab. Like one of the last steps, it says that you backwash the drying agent, and then it says that you're supposed to heat them. You're supposed to heat like the solution that you made, right? Not the backwash stuff.
Well, the backwash is going to go into the first.
Yeah. Okay.
Yeah.
So
Then you're going to evaporate that in a 3-way beaker.
Okay. Because like when I was reading it, I'm like, it doesn't make sense to heat the drying stuff, but that's what it looks like. So I was like super confused.
No, you're not going to heat the drying agent. The drying agent is there to dry the extract. Pour your liquid off, then you rinse the drying agent with some backwash. Anytime you transfer, you want to backwash it, so you can transfer 100%. If you pour coffee out of a cup, is it completely out of there? No, usually you have to rinse it once or twice to get all the coffee out, right? A backwash. You want to get complete transfer when you're transferring, or your yield will be diminished. I hope that answered that. If not, ask again after class or something. It's about that time. We'll get started. We ended with thermodynamics. Let's start there. 2 reactions, NF3 going to nitrogen. Decomposition of NF3 or Ni3. Which reaction gives off the most heat? Ni3? Yeah. What's the numbers? I did it myself. I got, for the Ni3, I got negative 381 kilojoules per mole. Is that what you got? So it's exothermic, gives off that much heat or energy. What about NF3? It's actually endothermic. And instead of giving off energy, it requires energy. Is that what everybody got? Correct numbers?
Yeah.
Okay. Which reaction is endothermic? Well, NF3, because it's a positive delta H. Yeah. Which reaction is fastest? Why Ni3?
The overall energy is higher than the NF3.
I agree that it's exothermic. What do you mean by the overall energy is higher than?
Isn't it impossible to determine that the energy of activation?
Yeah, pretty much. Yeah, I think it's hard to determine. For example, a diamond reacts with oxygen very exothermically. If you do the calculation, it'll be very exothermic. Does that mean it's going to happen fast? No, it happens quite slow. So slow it doesn't happen. Here, though, we can make an assumption. The assumption we tried to make last time is that the transition state leading to a lower energy intermediate will itself be lower. That's sort of an assumption. Now, we're not going to an intermediate, we're going to final products. But what we can say is the transition state leading to lower energy products will be lower itself. You raise the energy of the products, you raise the energy of the transition state. That's an assumption we're going to usually make. Sometimes it will be wrong, and I showed the example when it was wrong. But if we go with that assumption, here's the take-home. It's easier to fall downhill. Which reaction falls downhill in terms of energy? Ni3. You're going it's exothermic. It's easier to fall downhill than to fall uphill. Think about the stairs. You go to the top of the stairs, all you got to do is bend your knees and you'll fall down. It doesn't take much activation energy. You go to the bottom of the stairs, you're going to have to do some work to get to the top. It's easy to fall downhill. Based on that assumption, I'm going to say the faster one is the Ni3. Very exothermic, probably not going to take much activation energy. Are we correct with that assumption? Well, I've got a video of it. We'll see. Are the reactions driven by entropy or not?
Yes.
2 going to 4.
Yeah.
Yeah, so it's driven by entropy. That's a balance, or you can say 1 going to 2, but I balanced it for you. I got a video here showing the Ni3 decomposing to nitrogen and iodine. Okay? We know it's exothermic. Let's see what it looks like. Is that right? Okay, it's just going to be at the top. Can y'all see that? Okay. It should replay. Okay, at the beginning they got 2 right there. See it? There's 2 of them sitting there. That's 2 little ring stands containing Ni3, nitrogen triiodide. All right? What are they doing? They're touching one with a feather. When they touch it with a feather, what does it do? It explodes. The reaction takes place with why does it explode? What does that mean, explode? The energy is being released. How much energy? It was written right there. What? Something we calculated it, right? That energy comes out in lots of ways. You know. How much activation energy does it take to set this thing off? Just the touch of a feather. That's not much activation energy, is it? Good question. That's usually asked. How do they even get it there? Ni3 is a solid. All it takes is a little activation energy to make the reaction form. What does it form? Ni3 is converted to what?
Nitrogen.
Nitrogen gas, which is gas and it's going to expand. And what else is formed? Iodine solid. What do we know about it? It's colored. What color is it? Purple. That's why the vapor is purple, because iodine's formed there. All very immediately. Why does the one on the other side take off and it didn't get touched by a feather? The shock wave. You know, it's enough to kick the other one off. How did they get it there? They probably had it cold. You had to keep this stuff cold. They probably had it cold. They set it up there cold, then they let it warm up. Then it was ready to go, and they just touched it, and a little bit of activation. Question?
So then how do you handle this compound? It's just like touching it will cause it.
Cold. Keep it cold. Let it warm up. You might lose a finger. You don't want to use too much. It's an explosive compound. We saw that delta 8, very exothermic for decomposing, for going to nitrogen and iodine. And our assumption's pretty correct. We go way downhill. We lose that much energy. It doesn't take much activation energy. If we graph that, we need to get here. Some arbitrary. Here we go with Ni3. Where we go? We're going way downhill. We're losing how much? 300 something per kilojoule per mole. So how much activation energy does it take to go downhill? You know, boom, that much, right there. I mean, I barely even showed some. You know, it's some, but apparently it's not like this. Small amount, touch of a feather, get over that hill. But how do you predict that? It's hard to predict. In this example, we see that it's apparently not that much. The NF3 compound does not do this, because that reaction is endothermic and it's just not that favorable. NF3 is very stable. Any questions about thermodynamics, kinetics? How can you camera? Okay, so that's energy that came out exothermically. Can we answer these questions? Let's look at the addition of HX to alkene. Basically, the alkene reaction handout. We've also got the purple handout. We need to start there. The purple handout shows our reactions. Roman numeral 1, second page, purple handout. These are first reactions we'll look at. Then we'll move to Roman numeral 2. Reactions of alkenes. The alkene has the pi bond. Because the pi bond is not held as tightly as sigma bonds, the pi bond electrons will react. Okay? Source of reactivity. Those electrons. We will react an alkene with like HX, make an alkyl halide. We'll react an alkene with water and an acid catalyst to make an alcohol. Alcohol, acid catalyst to make an ether. You know all the functional groups. This is synthesis. Okay? Lots of synthesis in organic chemistry, converting one functional group to another. Alkene converted to an alcohol. These are line reactions. We'll look at mechanism for each of these reactions. How the reaction takes place. There's general classifications of reactions, terminology you need to know. These reactions are called electrophilic additions because an electrophile adds to the alkene. What is an electrophile? Electrophile is something that likes electrons. It's on the warm-up page. The first electrophile we will use is H+. Reaction with H+. H+ is basically comes from a strong acid. Question?
So what's the difference between like electrophiles and Lewis acids? Is that kind of like the...
Nothing much.
Not much.
Nothing much at all. H+ is the electrophile. These reactions will involve a carbocation intermediate. What I want you to see here is on my handouts, I give you the information there. It's very important. If it wasn't important, I wouldn't write it there. So, electrophilic addition, important term. These are reacting with H+. Okay? That helps us know what we're going to be doing in the next three reactions, right? These involve an intermediate. What's it called? Carbocation. Okay? You've got to categorize your information so when you're ready to recall, boom, 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 there you go. And then like note cards, reaction of an alkene with HX gives what? Well, alkyl halide. Now, in a lot of cases, you don't memorize stuff. You just do the mechanism. Very akin to math. Okay? What's 25 times 13? Who knows it? Nobody. Nobody here knows that right now. I guarantee you everybody can do it. Okay? That's the way I want you to approach this. Do not memorize. Learn how to do it. We will learn how to do it by doing mechanisms. You learn the mechanism, you can do anything. You memorize, that's all you can do, and I guarantee you won't see that exact question on the test. Okay. Now guess what? We'll move down to number 2. Those will involve other electrophiles other than H+, and those reactions do not involve a carbocation. So I'm trying to give you some organization here. But you have to recognize that. You have to organize the material what's best for you, but you do have to organize the material. Okay, we'll refer back to this as we need. The good news is at the beginning we're going to work with one electrophile and it's H+. First reaction we'll look at is addition of HX to alkenes. First one right here, HX. All right, but I've got them over here on the written handout. Another terminology. When we're going to add HX, this is called a hydrohalogenation because we're adding a hydrogen, and we're also adding a halogen. So a hydrohalogenation reaction. React an alkene with HBr to a hydrohalogenation to give that alkyl bromide. Bromine is now in a tertiary carbon. We have added HBr to the molecule. You take this formula, C4H8, that formula now has HBr added to it. It's an addition reaction. There's only about 5 or 6 general types of reactions. Addition reaction is one type. Elimination reaction is another. We're not eliminating anything. We're adding to this molecule. What is the mechanism? Mechanism is where we're going to use mechanism arrows, sometimes called curly-headed arrows, to show movement of all electrons. You show formation of and breaking of all bonds. If a bond is formed or broken, you need to show an arrow illustrating that. Arrows do not show movement of atoms. Okay, mechanism. First off, HBr can either be shown covalently or ionically. Either way works for me. HBr is a covalent molecule, and when it's just isolated, you put it in something like water, it'll ionize, or ethanol, it'll ionize. Either way works in the mechanism. If you show it covalently, you can't show dipoles, and the hydrogen is partial plus. If you show it ionically, well, you got H plus there, formal H plus. These are electrons. The pi electrons, I said, will react. They're not held that tightly. Electrons have a negative charge. Okay? What do electrons like to be attracted to? Since they're negative, they like to be attracted to positive. Wow, that's a... All right. So, is there any positive nearby? What's positive about HBr? Is it the B, BR? No, the BR is either minus or partial minus, depending on how you show it. What's the positive part? H plus, or the dipole with the partial H, either way. If you simplify your line reactions, usually you're looking for a minus and a plus to come together. Okay? So, how do these react? Well, let me give you a little, hopefully somewhat illustrative attempt to demonstrate it. Pi bond here. Here's pi bond. Double bond, okay? Carbon-carbon, pi bond. One of these is a pi bond. Sigma and a pi. All right? You're an H plus. I'm walking down the road and I come close to an H plus, and these electrons, what do they start doing? For some reason, they're attracted to the H plus. Take physics or something, but they like it. They like it. Okay? Well, again, the pi bond's not held tight. It's loosely held. It's not strong. Okay? So they get attracted, okay, in something like this, but eventually they have to break away and they go bond. Okay? And that's what I'm illustrating here. Here, pretend like right here, here's the pi bond drone. Back over here is an H plus. I'm showing these electrons are breaking away from this carbon, not this one. And they sort of hinge. And they hinge up and they go make a bond to that H. That's what that arrow is doing right here. Hinging. Okay? Every time you move an arrow with your alkene, think of a hinge. Okay? Carbon, carbon. If I hinge, tell me which carbon, my hands or body, bonds to him over here. Hands or body? No, here's hands carbon, here's body carbon. Which carbon is now bonded to him? Body carbon. I pulled away from hands carbon. Okay, this is two carbons here. 1, 2. Electrons pull away from this carbon over here and go attack. Okay? This carbon is now bonded to an H. This carbon has one less bond. That isn't uh-oh. If I pull, somebody grab these electrons. These electrons, grab them and pull them away and go make bond to H. This is nothing really scientific here. This is just simplistically saying these electrons pull it and go make bond to H. Now that's bonded to H. Okay? Carbon now only has 3 bonds over here. It's now a charge. What's a charge? Positive. Okay, if you can count charge, and if you know that's not a standard carbon, it's only 3 bonds, it's a positive charge. What's the charge of this carbon? First off, how many H's over here?
2.
No, there's now 3, because how many there? 2. How many there now? 3 total. That's why there's no charge there. There's 3 total H's. That carbon's now, okay? I only drew in the new one. There's also 2 H's there that are undroned, right? That we began with. You got to know where your H's are. And many of you will always mess up and not keep track of your H's. Okay? And I have to remind you, you got to keep track of your H's. Okay? You want to draw them in at the beginning, draw them in. I'll typically draw in the new one. This is called a carbocation, right there. It's a carbon that's a cation. We shorten that to carbocation. Isn't that what we said would be the intermediate in these first reactions? Carbocation intermediate. This is your intermediate. There's only one intermediate in this reaction. Next, this bromine over here. How did we get it? Well, if you start ionized, it's already there. How do you ionize it? Well, you could draw this like this. How do you want to show this ionized? What happens when you ionize? The bromine takes these electrons?
Yeah.
So these electrons move on to bromine as a fourth lone pair, and what does this electron movement give? It gives that. It gives a bromine with 4 lone pairs and an H with nothing, that's an H+. I'll allow you to start with that if you want. We can also do this reaction this way. These electrons break away and attack the H, and at the same time kick these electrons off. That's suitable also. Either one of these gives the same thing though. Bond to H, the bromine is now like this. At this point, how do we get final product? These electrons, this atom is a minus, it likes what? Positive. We got a minus and a plus. How do we get a bond? These electrons make bond to carbon. And now we show the bromine bonding to carbon. The bromine has how many lone pairs at the very end?
3.
Only 3, because the other lone pair is now doing what? It's actually now bonded to carbon, as we illustrated with this arrow here. These electrons bond to carbon. Question?
So will hydrohalogenation reactions always be two-step reactions? Well, at least two-step reactions.
I'm afraid to say yes, but I think so. I don't know that really need to know. At this point, yeah. I mean, that's it. Okay. What's the electrophile in this reaction? H+. What's the definition of electrophile? It likes electrons. I'd rather say this, because I like electrons to be the active component. I'd say electrons like it. Electrons like electrophiles. All right? The electrophile is the thing that the electrons attack. H+ here's the electrophile. Br- is the nucleophile. What's nucleophile mean?
Electrons don't like it.
Electrons don't like it. What does it like? It likes the nucleus. What's the charge of a nucleus? Nucleophiles like positives. Br- like that positive. That's why it bonded to it. Okay? We will use that type of terminology throughout. Electrophiles are acting with nucleophiles. That's organic chemistry all the way. This is a two-step mechanism with one intermediate. We do a reaction coordinate diagram. What would that look like? We have reaction progress, some type of energy. We start with some type of just arbitrary level. Here, the alkene. That's the energy level of that alkene. We want to put all of our intermediates on here. How many intermediates do we have? Just one. Is it higher energy or lower than that? It's actually higher because it's charged. Okay, we're going to put it up here. This is going to be our carbocation intermediate. I don't want to clutter this up too much. Okay, draw you an arrow or something. That's the carbocation intermediate. After that, what do we come to? Final product. Final product is now neutral. It's going to come back down. How does it compare to this? We could get out our calculator and look at bonds broken, bonds formed, but let me tell you a qualitative way to assess it. On the left, we have an alkene, which has a pi bond. So on the left, we had pi bond. That was broken. What was formed? What's new on the... Sigma bond to H and sigma bond to bromine. We broke a pi bond, we made 2 sigma bonds. Should this be better or worse? This is better. Better in terms of stronger bonds. We made stronger bonds. So is this higher energy or lower energy? Lower in energy. So this reaction should be endothermic or exothermic? Exothermic, yes. But basically, product is lower in energy because it has 2 sigma bonds compared to the weaker pi bond. So I'm going to draw it lower. And this is going to be what, our alkyl bromide? Importantly, we'll see that the halogen is going to be on the tertiary carbon. Okay, how do we get there? We don't go straight here. What do? We have some type of activation energy with a transition state, yeah? That's your activation energy. What is the molecules look right up here? This is where, like, the bionic woman, remember? Or man, whatever. It's like, it's this process where the bond's being formed. Okay. That process is high energy, but once it's totally formed, we then fall into this energy well a little bit lower. There's the true carbocation in the energy well. Now, if we want to fall downhill, how much activation energy do we need to fall downhill? We don't need much. We just need a little bit to get over the hill. Two steps. Which one is the rate determining step? Yeah, the first one. The one with your highest activation energy. That's your slow step. Slow step is formation of what? Forming the carbocation, yes. Forming the final product, the bromine added to the carbocation, that's fast, relatively. Is it thermodynamically favored? Yes. Rate determining step, first one. Kinetically favored. What does kinetically favored mean? I'm not sure what that means. I think this was supposed to be entropically favored. Is it entropically favored? We already answered this, I think, last time. No. What are we doing? In addition, alkene plus HBr to give one product. 2 molecules coming together to give one. That's not favored by entropy. So would you want to heat this reaction? Is heating going to make it be better?
No.
No. Heating will make it reverse. And you can actually reverse these reactions. Okay, I'm going to try not to erase this because we're going to come back and add to it. Let's look at the reaction below. So there's a hydrohalogenation. Why did we not get this product? Why did we not react this alkene? By the way, what's the name of this alkene? 1, 2, 3. What's that? 2-methyl 1 propene?
Yeah.
Yeah? I think that's right. 2-methyl 1 propene. Why not react with HBr and get that product? Why does it not get that product?
Still have
Yep.
I'm going to not erase that, okay? I want to keep what I drew up there. I'm going to redraw that over here, I reckon. Lights off. If you can't see, let me know, but maybe the projector's better. For Br to attack out here, we must have had the cation out there. Where's the new H at? New H is there because, see, there's no H on this carbon. Now there's one. So there's the new H. That means that instead of the electrons breaking away from here, it seems the electrons break away from over there. And we hinged it this way. That is, like this. And now this is bonded here. Okay? It doesn't matter where you put the H. Okay? made a bond to H, leaving this as what? There's only two H's there. There's your carbocation. And then to get this product, Br minus would add there. And we can envision that. Similar mechanism. But why does it not go that way? It all has to do with the carbocation that's being formed. Which carbocation is more stable? This one, by the way, what do you want to call this one? That's a primary carbocation. That's a primary carbon with a cation, a primary carbocation. What kind did we make in the reaction above? It's up there at the top. Tertiary. Which carbocation is more stable? Tertiary. Why?
That's more carbon pushing electron.
Because if you look at, how do you stabilize a plus? Push electrons towards it. All this can push towards it. Okay? Let's just make it one carbon. This can push towards it, but if we have other groups on it, these can also push towards it. And so, ultimately, the take-home, the more substitution you have in your carbocation, the more substitution with sp3 carbons, which are donators, the more stable your carbocation is going to be. And this was on one of the questions on the test, right? One of the multiple choice questions. Okay. But it's nothing but just considering your inductive effects of your sp3 carbons, donating towards that plus, stabilizing it. Where here, you don't have substitution on that there. This is only one donation. Okay? The tertiary carbocations are more stable than secondary, and those are more stable than primary. The primary is more stable than CH3, because it doesn't have any sp3 carbons. That's your worst carbocations in terms of the ones that were originally tetrahedral. So if we plotted this same reaction here, where would we put the intermediate at compared to, that's the tertiary one. How we can put that there? Where would we put the primary one? It would be higher, right? Okay. So when this molecule reacts with the H, it can go that way or it can go that way. Which path is it going to take? It's going to take the lower energy pathway, right? Just like water running down the road. When it comes to a fork, is it going to go up the hill or down the hill? It's going to go down the hill. Water's going to go downhill. This is going to take the lowest energy pathway. The lowest energy pathway is to form which carbocation? Tertiary. And from there you get product. That's why you get the halide on the tertiary and not on the primary carbon. It all has to do with which carbocation you form. We call this reaction regioselective. That is, the bromine only bonds in one region. It only bonds, it burns at a certain carbon. Basically, there's other ways to say this. We can say only one, well, really only is not precise. I'll say it for now. Only one constitutional isomer form. What's the relationship between the product above and this product? Constitutional isomers. The bromine is connected at a different spot. We also say it's connected at a different region. This reaction doesn't give a mixture of both. It's selective for only one. It's selective for the top one. This reaction is said to be regioselective. Okay? Now I said it only gives one. That's really not right. All you have to do is favor one on the other to be called regioselective. This reaction favors that one over this one. But sometimes I may say it only gives that one and not this one. This may be formed in a very small yield, maybe 5%. But it's still regioselective because it's not 50-50. Favors one constitutional isomer over another. In the context of these reactions, these two are called regioisomers. In the context of the reaction. Regioisomers are just a specific type of constitutional isomer. Here's your carbocation stability. We talked about effect on reaction coordinate when I put this one higher. And so that's the way the reaction is going to go. Okay, let's see if we can predict products here. Now at this point, this is where I want to remind you. Don't rely on, okay, alkenes react to give hydrogen, hydrohalogenation. I want you to think this way. Alkene reacts to give what? Carbocation. Are you going to make the carbocation on the more substituted carbon or the least? More. And after you make the carbocation, then bond the halide to it as your second fast step. At that point, what you have on the paper will be your product. You don't have to memorize it from scratch. You just kind of work your way towards it, and there it is. You guys on my right do the one with ACl. You guys on my left do the one with HI. And everybody, we can do the third one together. So show products here. Got product for HCl. How's that look?
Good.
Well, you don't have any of your mirrors.
Don't have what?
You don't have any of your arrows.
Any of my
Arrows.
arrows for what? Do what?
The intermediate.
Well, all I wanted was the major product. That doesn't mean that I wouldn't recommend having everything there. I don't need it because I can kind of do it in my head.
You show it. You draw it.
But you could do it. Yeah. Let's go through it. What do you need to do here? What is the Alkane attack? H plus. Let's show this ionic. Okay, that's okay. Let's just start with an ionic. These electrons walking down the road, they see that H plus. What do? They go make bond. But importantly, are we going to hinge away? Are we going to leave cation on top or bottom? Because when these electrons break away, you're going to leave cation. We can hinge this way and leave cation on the bottom, or we can hinge this way and leave cation on top. Where do you want to leave cation? Top. More substituted carbon. Because a more substituted carbon would be like a tertiary carbon. That's more stable cation than a secondary. I'm going to hinge down. I'm going to take these, and that's the pi bond. I'm going to pull them away I'm hinging this down. So which carbon is bonding to the H, top or bottom?
Bottom.
Yeah, the bottom is bonded. And so that's going to give, now that's bonded to the H. We just made that bond to H. There's a methyl there. But what else is here? Is there anything else here that's not drawn?
Yeah.
No,
How many H's on that carbon?
0 right now.
0, because there's 0 there. We didn't add one. There's still 0. There's only 3 bonds. That's a plus. How many H's on this carbon?
1, 2, it's an additional one.
No, there's 1 there. We added a new one. There's 2 there now, okay? Now, I don't usually connect my bonds. All right, if we do this, I just take too much time, and it looks... All right, everybody be there. That's me, just not connecting my bonds. There we go. There's the new H. All right, boom. Made a bond to H, leaving out a carbocation. What kind of carbocation did we make? Tertiary, the best one. If we put it down here, it would have been secondary. Go back and do it. You'll see it. It'd be secondary. That's best. What's the next step? These electrons do what? Bam! Okay? Chlorine adds to carbocation. What do we get? Product I showed. Right?
So why didn't you move the hydrogen back up to the top?
I haven't moved it. What do you mean I moved it back up?
So the hydrogen over in your carbocation intermediate is bonded down to the bottom.
Yeah.
Oh, he just didn't draw it. Okay, I got you. Sorry.
How many H's on that carbon?
2. Yeah, you just did. It's fine.
Yeah, there's a new H here. I just didn't draw it in at the end.
Okay.
I did it here just to say, hey, we added a new H, but I don't have to draw it in at the end, do I?
No. I got you.
Right, as long as you get me in today and not 2 weeks from now,
Yeah.
right? I mean, if you want to draw in the new H, it's there. And what have we added to the compound? So you did an addition of HCl. You got to know where your H's are. You can't get confused when I draw one in or don't draw one in. Just, I mean, there. If there's no charge there, there's got to be another H. There should be because we added one, but there was one to begin with, right? Got to know where your H's are at. Okay, do we expect to get a product with the chlorine here and the H there?
No.
No, that would mean the secondary is just as good as tertiary. No. Is this reaction regioselective?
Yeah.
Yeah, it's going to be regioselective. That's going to be the preferred regioisomer. The preferred constitutional isomer. How about this one down here? You want to make cation on left or right? Yeah. See, this guy is going to hinge away. Well, I'm going to do it up here. It's going to hinge away, make bond. This carbon's going to bond, leaving that as the carbocation. When I draw it, it's easier to do here. These electrons, okay, I'm sort of pulling them away, going to make bond, leaving that as a plus. There's a new bond there. Sometimes I'll highlight new bonds with a zigzag line. Just made that bond. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Don't lose track of the number of carbons. See it all the time. 5 carbons here, all of a sudden there's 6 here. Where's the plus charge? See, that used to be alkene, right? With those electrons, it wouldn't make bond to H. Plus is here, right? There's your intermediate. We got a secondary carbocation. What happens next? I minus. Bam. And what do we get? Right there. There's a new H on the end, right? Because to begin with, there were 2 on the end. Now there's 3 on the end. We just did an addition of HI. We did a hydrohalogenation. We made an alkyl iodide. Various terminology that we could use. Do you need to memorize that one pentene reacts with HI to give 2-iodopentane? No. Questions?
Yeah. Okay, the first example when you were talking about the hinging, when you say hinged up, does that just mean that it did branch off the first?
Up here?
Yeah.
It's hard to hint. Pi bond is this way. What do? Well, I really need to do this way so I can break away. Here's the pi bond on the board, right? Here's that top carbon. Electrons break away from the top carbon and go attack H. So the bottom carbon attacks H, leaving the top carbon as what?
Positive.
Carbocation. So the electrons broke away from the top carbon, leaving it without the fourth bond. So here's the bond to H, here's the carbocation. Okay, do we expect regioselectivity?
Yes.
Or do we expect just as much product with the iodine on the end? No, iodine on the end would have come from a primary carbocation. That would be higher in energy and less likely to form. How about the third one? You want to make cation on the left or right of the alkene? Either way, it's going to be what type of cation? Yeah, either way, it's going to be secondary. If you pull away from that carbon and like take these electrons, pull them away, UH here, cation there. Or we can sort of go the other way and sort of pull them away from that carbon. Sort of make bond here, leave that a cation. What type of cation is this?
Secondary.
What type is this?
Secondary.
Which one's preferred?
Neither.
The inner one.
I don't see much preference here.
So it's not regioselective.
This reaction is not going to be regioselective. You're going to get two different products here. Now, in actuality, you may get 52% of one, 48% of the other, and you can call that regioselective. But in terms of us, no. It's not going to be that good. Let's draw both products. We'll get one product with the iodine here.
And the other one you have.
Oh yeah, it's yeah, very similar. This reaction is going to be regioselective and only give that one. The bottom reaction actually gives both. Neither one is going to be like highly favored. I know there's a couple of questions. Let me say one more thing. So, if you wanted to make this product here only, what is that, 2-iodopentane? Your goal is to make that in the highest yield because you want to make the most money. Which reaction would you use to make it? The top one or the bottom one? Top one, obviously, right?
Right.
Because the top one gives only that, or mainly that, where the bottom one is going to give a mixture. This is not preferred at the bottom. They're both kind of. This reaction is said to be regioselective, this one not. Questions?
So when we show the electrons like attacking the hydrogen or whatever, like grabbing it, does it matter like which way we curl the arrow, like showing?
No, top to bottom.
Okay, you don't care.
It just needs to be clear.
Okay.
What I prefer not to see, because when I see this, I'm like, I don't think you really know what you're doing, is to just kind of draw something like that. I'd rather you see the hinging, because to me, when I see the hinging, I see, okay, this person knows that they're breaking away. To me, I think you're just doing this, and that's about all you know. Now, why does it matter? Because to me, the more you know how to do arrows, the more you're going to be able to do it correctly. Yeah, I would prefer that you show this as if you walked up here and grabbed these electrons, and what do you want to do with them? You want to pull them away from which carbon? Well, let's do this one. You want to pull them away from which carbon?
The top one.
The left one. You want to pull them away from the one on the left. So I'm going to kind of grab it over here and pull it. So like hinging it away and leaving them. But if you will, every time I do the arrows, I know you guys are seeing the big picture for the first time, but I try to do everything very precisely. Okay? Look back on the videos. You got to practice your precision and really understand. Let me tell you this. There's two types of questions here we're dealing with. Predict a product. You're asked to predict a product. You don't need anything else other than this is the product. But I would recommend, just like in math, if you're asked to give the answer to a problem, you probably do a lot of scratch paper work with your formulas and stuff, right? Well, here you're on your scratch paper, you're going to be doing your mechanism. Working everything, and here's your product. The other type of question is actually a mechanism question, where I give you the product and say, okay, show the arrow movement. And looking at, can you move arrows correctly? Can you show intermediates correctly? And once we start doing variable mechanisms, can you give the right mechanism? Question?
Can you explain the hinging for the second question? I mean, the second example.
Here, the hinging? Well, if you go either way you hinge, you're going to get a secondary cation. And neither, I mean, there's no preference.
So you would draw it like middle?
No, you would have two different. It can hinge, you could pull away from there. What does that mean? The electrons are being pulled away from that carbon. The new H is here. The new H is here, and that's plus. Because right here, it's like you took these electrons and pulled them away from that carbon and went and made a bond to H. Yeah? That's what the arrow means. So now this is bonded to the H, but that has lost its pi bond, it's plus charge. Okay, at some point there was a question. No, we haven't gotten it yet. Synthesis, going backwards. Provide a high-yielding, regioselective synthesis of the following alkyl halides using a hydrohalogenation reaction. What I'm asking you for here is what would be the starting material and what would be the reagents? Now, hydrohalogenation, that means we're reacting something with what here? HBr. So what would we react? Well, guess what? We're reacting alkenes right now. What's the alkene going to look like? Some T? One protein? One protein? Propene? So here. Why that and not two propene? I mean pentene. Why not two?
That's not high yielding.
Because it can do either or.
Because it's not regioselective.
This is not going to be regioselective. Are you going to make cation on left or right? Either. Either will be secondary. That's not going to be selective. This is going to be the selective one. You're only going to make cation where? Over there. So the H plus, these electrons are going to hinge away. See, I hinge them away in an attack. Okay? This carbon bonds to this. And we end up with that carbon bonding to the H. This is plus. We're going to make secondary cation. We wouldn't put cation out here. We wouldn't make primary. And from there, the Br minus, these electrons attack and make your sigma bond and your home free. So that one, not that one. How about the one with the chlorine? What alkene would you react? Question?
Well, if we draw our positive sign in the correct on the correct carbon, do we have to draw the hinging motion of the arrow?
Well, you got to have an arrow because you got to have an arrow for all electrons moving.
But
You need an arrow for formation of every bond and breaking of every bond. You made this CH bond. You gotta have an arrow for making it.
we have to draw from that one specific spot that you said, like, you have your 2 circles.
I'd have to see your alternative of what I did here.
Just a straight line.
Again, I mean, I'd rather see some hinging action so you know. I just see too many students who just are drawing arrows but really can't explain what you're doing. If you know what you're doing, then it's good for me. If you get the right products, it's good for me. So what's the alkene over here? Let me see. How about that? This high bond is right there, yeah?
On the right side?
Could it not be on the other side as well?
Like there?
Yeah.
Well, that's the same thing.
Okay. It's just a mirror image. Kind of.
Well, it is a mirror image, but it's also the same thing. Because some mirror images are not the same thing. What's the name of this? 1-methyl cyclohexene.
That's the only thing.
Either way you want to draw it, it's the same thing.
It's like the same thing as this. It's like basically 14 this one.
Because when this attacks, where are we going to leave cation, on left or right? See, I'll say that for the next 2 weeks. Where are we going to leave cation, left or right? Left, tertiary cation. And then the chlorine attacks there, yeah?
This one.
You're not going to, I mean, we're not going to break away from that carbon. Put cation over there, would we? Put new H here? No. We want to put cation there, so we want to break away that way, put new H there and cation here. Somebody get something else here? And also alkene up like that, to the top carbon. Who got that? Everybody see it now? H plus. Are we going to leave cation on top or bottom? Top would be primary, bottom would be tertiary. Let's pull away from the bottom. Oh yeah, this is how they do it in medical school. One hand here, one hand here. All right, you gotta get, yeah. So we're hinging up, putting new H up top, leaving what here? Cation. 2 H's there, and there's now 3 up there. Chlorine attacks.
What would you do if you did it the other way where the cation wasn't on primary carbon?
Put cation up here.
Yeah, exactly. So if you were to
Put
do
H
that,
here.
how would it would just
Or you'd pull away from the top.
okay.
We're not going to make cation up top. Question? Question?
And like, if we were given a problem like this, are we gonna like show both the double bond and one? That's like, are we supposed to show both like the reactants? Like the one with the.
I'm just showing, there's 2 different alkenes that could react to give that product.
So you want us to show both?
This and this. Depends on the question. If I asked you for one, then either wouldn't work. If I asked you for both, then show both. Question?
Isn't technically the alkene that like, as the thing coming straight, isn't that technically higher yielding? Because it's 1 versus 3, it's primary versus tertiary versus secondary, or no?
You could argue for even more selectivity here,
Okay.
perhaps. I haven't gotten into that. Any questions about these? So really for this one, there was not an alkene that would not work, was there? I mean, we showed alkene there, alkene here. There's no alkene that would not, I mean, you can't put alkene here because, at least for now, we're adding HCl across the pi bond. So if you got alkene here, the chlorine's going to need to be here or here. Now, as we move forward, we'll see that we can do some rearrangement, some shifting. Let's take a minute to look at the one below. It's got an interesting little additional thing to consider. Which product do you think is favored down here?
Yes.
And really, what is really the question I'm asking? Really, the question is which intermediate is favored down here? Because whichever intermediate is formed, that's what gives the final product. The question is, would you rather put cation on top or bottom?
No, negative.
If we put new H on bottom and cation on top, we get that. If we put new H on top and cation on bottom, we get that. Which cation is more stable? This is tertiary, I agree.
Secondary.
Which one's more stable? This one here is actually more stable. Why?
Is it negative and positive like each other?
Why is this one more stable? It starts with an R and ends with resonance. Yes. Resonance is usually a better stabilizing effect than just carbon induction. Resonance, because these electrons next door. Let's talk about hybridization here. What's the hybridization of this carbocation? sp2. Okay, there's a p orbital here. It's actually empty. What's hybridization of the oxygen? sp2, because anytime a lone pair is next to a p orbital, the lone pair is going to want to be in a p orbital, right? sp2. So one of these lone pairs is in a p orbital. The other is trigonoplanar with the methyl and the other lone pair. But what is that one lone pair doing? It's conjugating with the empty p orbital next door. That's a very stabilizing effect. If we illustrate this by drawing resonance structures, we would do it like this. There's the original plus charge. How do you stabilize a plus? Move electrons towards it or away? Towards it. These electrons can be moved in here like this, and we can get an alternative Lewis structure. It has double bond to oxygen, methyl, one lone pair, and now the plus is on oxygen. What we have here is a resonance, this is called resonance structure. The charge has been delocalized. The charge is not just sitting on the carbon, but some of the charge is on the oxygen now. This is a resonance stabilized carbocation. Very often resonance is better than your inductive effects. Questions?
Would you factor in the oxygen's electronegativity? Because if you have a carbocation, like in like that position, would oxygen be pulling electrons away from that area
Yes,
to make it less
you have two effects here, and they're counter to each other. Oxygen inductively does what? Induction means sigma bond, and when you do sigma bond, you're just dealing with electronegativity. Oxygen pulls inductively, but because it has a lone pair, it donates by resonance. And with oxygen and nitrogen, the donation by resonance is the greater effect. This is the first glimpse at resonance stabilized carbocations. Okay, we'll see some more. The preferred product is actually which one? Well, this is the preferred cation. So which is the preferred product? Yeah, that one. Resonance stabilization of a carbocation. Okay. As we move through these, now we're going to move to another reaction. Hydration of alkenes to give alcohols. This is a reaction you're doing in lab this week. Look at the purple sheet. We just did the first one. We're moving on to the next one. Here we're going to add water to the alkene, give an alcohol, but we have to use an H plus catalyst. Here the H plus will be catalyst. Alkenes do not react with water, pure water. No reaction with pure water. The skin of an apple has many different alkenes in it. It protects the apple from the rain. It doesn't react when it rains. Okay? Now, if we get some acid rain, we might get a reaction because this reaction is catalyzed by acid. If we add an acid with the water, we can get a reaction where water is added to the alkene, so we're doing an addition reaction. They're all addition. That's the first heading on the handout. Formula now has water added to it. There's a new H there on the end, and so there's your H2O. We say we've added water across the pi bond. Across the pi bond. Requires an H plus catalyst. Of course, water plus H plus is often shown as H3O plus. It has to be a strong acid or a pretty strong acid. Example acids are going to be sulfuric, phosphoric, or HF. We will not use HBr or HCl. Because if you use HBr, it doesn't do this. It does hydrohalogenation. So you don't want to use HBr as your acid. You'll get a hydrohalogenation product. HF won't give a hydrohalogenation product. Basically, we'll state this again. None of these acids here, the minus of none of these will ever do anything. We don't want it to do anything. We want these just to serve as H plus source. We want water to be the nucleophile. Okay, let's look at the mechanism. Well, this supplies H plus. You can show it ionically if you want to begin with. So here we go. We got H plus again. Just like before, the alkene can react with H plus. Oh, look, when we react, you're going to leave cation on left or right. Correct. Leave it on the left, because that would be a tertiary. And so we're hinging away, going to attack the H plus, leaving cation there. Go make this bond. Okay? So the first step is nothing new. Now again, these electrons won't attack water. They will attack H plus from a strong acid. Now once we get the cation, water is what attacks here. Not a halogen, not the minus here. Remember, none of those minuses will ever attack in this class with me, or organic 2 with me. That's why we use those acids for just acid catalysts. But we do have water because those are all aqueous acids. You got to have water here. These electrons then add to the cation. Bam. Oxygen makes bond to carbon. What do we get? We get this here. A lot of students will just show this and all of a sudden have the product. It's not right. The oxygen has 2 H's on it. It still has 2 H's. You can't just lose an H. But now one of the lone pairs is bonded to carbon. We now have this intermediate. So I'm showing 2 intermediates, a tertiary cation, and this is another intermediate. This oxygen is atypical, it has 3 bonds, 1 lone pair. How can we get it to this point, which is final product? It has to lose an H. Now, I will see arrows that look like this, as if 2 electrons are just jumping off into space. That's no good. How many lone pairs on the final oxygen? 2. How many here? 1. How does it get the extra lone pair? These 9. How we're going to show this is, first off, I'm kind of taking liberties here. If we draw this out, there's a full Lewis structure. These electrons, every time you move an arrow, you say what? These electrons bond to H. These electrons do what? Move on to oxygen as the second lone pair. Okay? I see lots of students don't even show this arrow. But with a mechanism, you have to show movement of all electrons. That's how the second lone pair gets there. So these 2 arrows should mean something. What does that mean? Oxygen bonding to H. What does this form when that bonds? Yeah, you can show a full structure. What does this arrow mean to you? We just said it. The electrons moving on to oxygen as a second lone pair. So ultimately, we sort of started with sulfuric and we reformed sulfuric. We reformed catalyst. We reformed that H+. This is essentially H+. Now, you could use water to do this. You could use another molecule of water to take the H. If water takes the H, you form that plus what? H3O plus. That's actually strictly more correct because how does sulfuric acid actually exist in water? That's how it exists. But for me, I like to reform the actual catalyst that would be like in a balanced line reaction. What were the reactants here? H plus and water. What did we add to the molecule? Just water. The H plus was reformed here. It's a catalyst. In the first reaction, the hydrohalogenation, the H plus was not a catalyst. It was all just added. Now, this reaction here is reversible. I just mentioned that here. We're not going to do much with it. During test 2 or organic 2, we will do the reverse reaction. What is the reverse? Well, what's the forward? Alkene converting to what? Alcohol. You hydrate the alkene to make an alcohol. The reverse would be dehydrate the alcohol to the alkene. You have to remove water to make the alkene. Question?
So are all hydration of alkene reactions reversible?
For all which ones?
Like are all hydration of alkene reactions reversible, or
Hydration of alkene, yeah, hydration of alkene is reversible. What we got left here. Let's see if we can predict the products here at the end. Then as you look ahead for next time, there's a number of questions like this in the next few pages. Please try to work these. Okay? We'll be moving on to other reactions. Please be reading about him and then trying to work these problems in the next few pages that I give. Let's do these here, then we'll pass back the test. Okay, what's the H3O? What's the electrophile here? What's the alkene going to react with?
H plus.
I see water and H+. Alkenes don't react with water. Not as this first step. H+. It's reacting with H+. Okay? That's the only thing we've reacted with an alkene thus far, and that's Roman number 1. Are we going to make cation, left or right? On the left. Then what attacks the cation? Water. But then you have a positive oxygen and you have to remove a proton to go neutral. Removing the proton is essentially reforming the catalyst. I'm not going to draw the products here because we're about out of time, but you need to have these next time. And also look ahead. Down here, ethanol is just like water. It's a neutral oxygen. Alkenes don't react with ethanol. But that's an H+ source. Alkene can react with H+. Where are you going to make cation, left or right? On the left. What attacks the cation? In this case, not water, but ethanol. There's not much difference between water and ethanol. They're both neutral oxygens. Ethanol just has a carbon on it. After it attacks, what do you have to lose from the oxygen to go neutral? You lose the H. You're not going to lose the alpha. You reform the H catalyst. Please do both of these and have your products. Also, we need to consider stereochemistry. Okay, we'll pass back the test. I'm going to do it by sections. So when I call your section, if that section would sort of come on down a little bit. The high was 113. I'm sorry, 103. The low was 23.
Michael Jordan.
Good number of A's. There was another triple digit. I think there was 100 or 101. I don't do averages, but it was pretty average.
How is the average? Pretty average.
Key is posted. I'm going to turn this off.